Alright, welcome back to the algorithm analysis slides. Let's continue and finally mathematically say what it means for a function to be big O of another function. Are we ready? I think we are. So, we say, like we've learned this, we write that a function f is big O of another function g. We read it as f is O of g or f is big O of g. And here's what we learned about in 41. This is the way that I teach it. This is probably the way that a lot of instructors like to talk about it. It's a very hand-wavy definition, okay? So it's essentially saying that g is bigger than f for some meaning of the word bigger. And it's like g grows faster than f, and it's a simpler function, so it's nice, and we can talk about g instead of saying this very long and complicated function f, okay? So here's our hand-wavy definition of big O. It's like f of n is less than g of n if you drop all the constant factors and only worry about very large values. So like here is g of n is always bigger, something like that, okay? Or really, let's draw it down here. Here is f, here is g, it's always bigger, and it's simpler to talk about, okay? And we drop all those constant factors and all those lower order terms, and we worry about large values of n. It always is true that g wins out. G is bigger, okay? And then if there's only a constant there, it's O of 1. The constant becomes the number 1, essentially. Those are equivalent. So what does this mean? Like, how is this 1 a function? Well, it's just a function that always gives back 1. G of x is equal to 1 always for any x. So it's always a function. It's really a function is big O of another function, and we calculate like what this should be based on f by dropping all those factors and getting rid of constants out in front of things. But now let's talk about what it really means. Okay, here's the real definition of big O, and this is going back to asymptotic growth. Keep that in the back of your mind. Here's the real definition of big O. So f and g are functions, so assume that they are functions, and they take positive integers to positive reals, okay? This is a standard way of defining this. So you can never have negative values, or you can never have negative inputs. So this is what happens. Then f is big O of g if there exist constants c and n naught such that f of n is less than c times g of n. So for the same input, g wins out when being multiplied by c whenever n is greater than that n naught, okay? So before we get to the math, let me translate this to a diagram. So it's saying that here's f. As it grows, it might be all wobbly at the beginning, but eventually, if for a good picked constant, c, for a nice one, eventually there's a point, call it n naught, such that c multiplied by the result of g of n always wins out compared to f. There is a point from n naught onwards, for that value of x onwards, that c times g of n always wins, so that lets us know that c is bounding above f. F is bounded above by g with this appropriate constant, okay? So technically, maybe g of n really is down here, but multiplied by that constant, it gets moved up, and it always wins compared to f, okay? So in math, it's like, okay, there exists a c greater than or equal to 0. There also exists an n naught. There also, for those two values, it's always the case that for every number n that is greater than n naught, this is true. F of n is smaller. So g of n times that c wins out compared to f, okay? See, I'm reading that. So there exists these two constants such that this is true. It's always the case that no matter what number you pick, greater than or equal to n naught, from then onwards, g wins out when multiplied by the constant c, okay? That is what big O means, really. That means g is an upper bound for f, and with an appropriate c value, okay? So for example, this is why you get to drop all these constant factors. This means that f of n, if this one is 2n squared, it is definitely O of n squared, right? F of n is totally O of n squared, because you can pick a constant 3, it's always bigger than 2n squared, yeah? For example, and this is how you'd prove it. You'd be like, let g of n equal n squared, and then let C be 3, and n naught can be 0 for all we care. It's always going to be bigger. Okay, so that is how you formally prove that f is O of some other function. Okay, and because it's an upper bound, it's also true that 2n squared is big O of n cubed. 2n squared is big O of n to the fourth, because those are always bigger, right? You can choose an appropriate constant to multiply by n cubed and n to the fourth, such that this is bigger than that, because of course it's a faster growing function. Okay, so that's what big O really means. That's what it's talking about. All right, and let's get some more intuition behind why it's useful. Like, why do we care to find an upper bound? All right, so again, what big O is meaning is it's, okay, we found a function g that bounds f. F is bounded above by g up to a constant factor asymptotically as it grows and gets large. Okay, maybe not at the beginning, but later. Later it grows and g always wins out when multiplied by that special constant. Okay, there's always that caveat. So, for example, let's go back to this one. Like, here is our function, 2n squared. Let's use x instead, because I'm about to use a graphing calculator. So let's say that our function f of x, is 2x squared, and we have just proven, right, mathematically, that f is O of x squared only. We can drop the 2. And the reason we care, and the reason we want to say things like that, is because, really, those two functions, if you graph them, they don't look very different when you make n large. That's what big O is really trying to say. So let's use this graphing calculator. Let's be like, f of x equals 2x squared. So there's f. And here is g of x. G of x equals just normal x squared. Yeah? So here's the normal version of this. But if I zoom out enough, what do you know? It looks purple because the blue and red are right on top of each other. There is no difference for big enough values of x. Okay? There is no difference. They're essentially the same. They essentially grow the same. That's why we like to use big O. Like, we found a simpler function that lets us talk about this original one. And they, for all intents and purposes, grow to be the same. Okay? That's the idea. That's the whole point of this. Okay? So I just graphed this. Like, f of x was 2x squared, and then the g of x was just normal x squared, right? And yeah, that was what it means graphically for a function to be big O of another function. Essentially, they grow the same. They essentially look the same if you zoom out. Okay? Alternatively, if you've taken calculus and remember limits, you can say this. There's an alternative definition for big O. F is big O of some function g if you take the limit as n goes to infinity, dividing f by g, that is less than infinity. Okay? So g is able to bound f. Dividing f's result by g, g is big enough to bound f so that it doesn't run away to infinity, this quotient. Okay? That kind of helps you see how g is essentially the same as f. It's bounding it in a certain way that lets its result never run away. Okay? That is an alternate definition if you've learned about limits. So that is some more intuition behind big O. Hopefully it makes some more sense now. And at the end of the day, if you're given test questions about this, just follow the rules, right? It's you drop your lower order terms and you drop constant factors and you found a correct value for a function that is big O of another function. Okay, so for example, if I have this one, f of x equals 2x squared minus x plus 3, well, if I drop all the lower order terms, it's this guy and this one, goodbye. Now we just have 2x squared left. And then we drop the constant factors because we can always add them back with our special c value. So then there's that. Okay, so it's just g of x equals x squared. And so f is O of x squared, right? Because the variable is being used is x, it's not n. So if we want to get technical, why is this true? Why is f big O of x squared? Well, if you pick your constant out in front to be 3, for example, and your n naught to be 2, I did this ahead of time, it's always the case that after n not being 2, which is essentially the first value of x you can pick, after 2, then it's always the case that x squared is bigger multiplied by c. It's always bigger than this one. So starting at 2, for example, what's f of 2? That's equal to 2 times 2 squared minus 2 plus 3. Right, so that's 2 times 4, which is 8, minus 2 plus 3, which is 6, 7, 8, 9. So that's f of 2. What is g of 2? Times that constant, right? C times g of 2, because you always have that out in front. That is equal to x squared, right, times our constant. So x squared is 4 times 3, 2 squared, times 3, which is 3 times 4, which is 12, and it's bigger, greater than or equal to. Okay? And then as you get bigger for values of x, it still wins. Okay? So that's essentially the proof for why this is true, but if you just follow the rules, you'll always make the right answer. Okay? Same for this one. Where are the lower order terms here? Notice that this is a function of n, and this is also a function of n. They're multiplied together. So it's 2 functions of n at once. It's like n to the 3/2 or something similar to that, right? It's bigger than n itself. It's bigger than log base 2 of n itself. So this is a lower order term. So we can chop it off, and then here's a constant we can also chop off. But anything involving n needs to stay, right? Because that's the variable of the function. Okay, I used to use x, now I'm using n. Remember what the variable is. So it's not always n. F is equal to big O here of n times log base 2 of n. So that's my function. And you can find an appropriate c and n naught value such that the original definition of big O works for it. Okay? And then finally, one last big one. What in the world is a nice, smaller, easier to think about function compared to this one? Okay, so we're going to drop the lower order terms and also constant factor. So goodbye, goodbye. It's not out in front anymore. So this one wins, and then we have constant 3 that we can take away. So f here is big O of just x to the 42, which is much easier to think about. Yeah? So that is how that works. Okay. So yeah, we've just found a bunch of functions such that after a certain point, like here's f, here's g, f and c times g, there's our n naught. We found there's always a certain value for which g always wins out compared to f. Okay? That's big O. So let's do this a bit more mathematically, like this first example that I gave here, so that we can remember those rules and remember the math at the same time. Okay? So if we follow the rules, here's our original function f. It is big O of n cubed, because that's the one out in front and dropping any factors. Let's prove that f is equal to f is big O of n cubed using the definition. So this means that we need to find a c and we need to find a real n naught and prove that it always works. Like, this is a real proof now, no more hand waving. And in order to find a c and an n naught, here's a good process. If you're not sure what to pick, start with the original function and let me show you how to manipulate it in a nice way. So start with 2n cubed minus 4n squared plus 7, and then we're trying to get to n cubed, kind of, but we're trying to find our constant factor, we're trying to find our n naught, all that stuff. We need to find a function that's bigger than this, that looks kind of like it, okay? So this is always the case that this is less than or equal to, well, this was minus, let's make it a plus. 2n cubed plus 4n squared plus 7. This is always true, right? Always. And then let's find a bigger function than this. What if, and that looks more like this one that I'm trying to find a constant factor for and an n naught for, what about this? Let's change, well, let's keep this n cubed. Let's change this to n cubed. And let's also put an n cubed next to the 7. Yeah? 2n cubed plus 4n cubed plus 7n cubed. You see how that's a bigger function usually? but not quite when n is 0, right? When n is 0, these go away and it becomes 7. When n is 0, this all becomes 0 now. So that's not true anymore for it to be bigger. But once n is 1, right, this is true when n is greater than or equal to 1. This works when n is greater than or equal to 1. So let's remember that. That may be our n naught. And this, at the end of the day, is just equal to, right, boop, boop, that is 13n cubed. Do you see what I just did? I have found a constant to put out in front of n cubed. That's my c. And I found when that constant makes it always bigger than the original function from n equal to 1 onwards. So that's my n naught. That's when it starts working. And that's the proof. You can be a bit more technical when you're doing this for real on paper in homework, but this was the truth, right? We started here, and we got to something involving only n cubes, and we notice, like, when this is always true. Like, this is always true no matter the value of n. This is now always true once n is greater than or equal to 1, and then I can just bring them all together, and here's 13n cubed. You see that trick? Yeah, just make everything in terms of n cubed, that thing that you're trying to find, and that will help you notice a good value for c and for n naught. Okay? There's plenty more. Like c could be any bigger number, n naught can be any bigger number as well. There's infinite options, but here's how to find one of those options. Okay? Well, let's keep on trucking. I also said, I just kind of swept it under the rug, like, okay, if you have a function 2n squared, that's O of n squared, and O of n cubed, and O of n to the fourth, because like those are all bigger, right? Surely it's going to work. It's going to be an upper bound. Let me prove that to you. All right, so let me get a pen back. Assume f works like it takes positive integers to positive reals, and that means we can use big O on it. So we want to show that if we have this, if f is big O of n, if it grows linearly, then it also is bounded above by a quadratic function. F is big O of n squared, just as easily. Okay? So it's an if-then statement. If this is true, then this is true. So we'll prove it using a direct proof. We will assume this assumption. And then this is our conclusion, what we want to show. Okay, so we'll assume this, prove this. And here's our proof. Here's a way to prove it, at least. So let's get all the stuff that we know about. Let's assume all the things that we need to assume. So let f be big O of n. Then, if we unpack the definition of big O, we know that we get there exists a c and an n naught, such that for every n greater than or equal to n naught, we have that f of n is bounded above by c times g of n, which is just the function n, right? G of n is the function returning n, so it looks like that. So that's what we have, that's what we know. And let's prove that f of n is also big O of n squared, okay? So we'll end up keeping the same c, and I'll show you that the same c will work. Keep the same c. We need to show, assuming we do that, that there is some, to follow this definition, right? There is some c, we found it, let's just pick the same one. There is some n naught, I don't want to use the same name, so let's say n naught prime now, such that f of n is less than or equal to c times n squared now for all n greater than or equal to n naught prime. Okay, so just a different variable. And now what I want you to notice is if n is greater than or equal to 1, watch what happens. If I know this, another way to write that is 1 is less than or equal to n. Then I could multiply by c on both sides, so I have c less than or equal to n. And then I can multiply by n on both sides. I have c times n less than or equal to c times n squared. Oh, oops, I'm supposed to multiply by a c there too. So multiply by c first, and then multiply by another n. I have this, right? So if that's true, if this is true, then I can go from that to c times n is less than or equal to c times n squared. And if you put this together with this, let me put those in rainbow, this combined with this just proved that f of n is less than that. Ooh, that's pretty much what I needed for proving that something's big O. Isn't that cool? So therefore, yeah, we just did it. Therefore, f of n is big O of n squared using, let's say that we're using primes, right? C prime for this definition of big O, that's equal to the original C, and n naught, well, starting at 1, this is always the case, so that's one way to do it. But it's also possible that this n naught was huge, like f of n didn't really get bounded above until the original n naught was super large. And so I think that to play it safe, we have to say something like this. N naught prime is equal to the max of the original n naught and 1. Okay? So if n naught was super small, we know this is going to work when n is greater than or equal to 1, but it may have been the case that this took a while to take place, okay, before c times n won out, and so we'll pick the bigger one in that case, okay? That will prove our theorem. We have just proven that we can always find a c and an n naught to make this true whenever we have this true. So it's always okay to try something bigger. The bigger function always dominates still. Okay? So that is an example there, and that is how you prove stuff in terms of big O, using big O. So now it's your turn. Let me give you a proof that is very similar to what we just did. You're going to have to find those constants, okay? So here is your proof. So let's let f of n be n over 100. Why not? Taking positive integers to positive reals, totally fine. Prove that it's not true that f is big O of the square root of n. So this is not an upper bound for this function, sadly. Okay? Because this is like linear, and this is like n to the 1/2, right? It should be, once I say that, it should kind of make sense, right? But you have to prove it really using the theory. So your hint is use proof by contradiction, okay? To prove that it's not true that this is the case. It's not true that f is bounded above, that f is big O of square root of n, okay? So give that a try. It's a great practice example, and then I'll do it with you down here once you're back. All right, so using proof by contradiction, that means that if we want to prove that it's not true, well, what's the negation of that theorem? Well, let's assume that it is true that this is the case, and let's derive a contradiction based on that, okay? So the first step of our proof is assume f is big O of square root of n. Sure, that's okay to do. And then we're going to derive a contradiction, which means that this assumption was false. All right, so if that is the case, let's just go along with it. So there exists a c and an n naught such that, got to unpack the definition, such that this is all true. N over 100, because that's the original function, is, that is f of n, right, is bounded above by c times square root of n, because that was this function here. That's g of n. C times square root of n for all n greater than or equal to n naught. Did you find the contradiction? How do you derive a contradiction here now? So, okay, we just know that n over 100 is less than or equal to this, c times square root of n for some certain values bigger than a certain starting value, c times square root of n. All right, let's do some math here. Let's bring the square root of n on this side and the 100 on this side. So I'm going to multiply by 100, and then bring the square root of n over here. So remember that this is n to the 1, and this is n to the 1/2. So that gives me, maybe let's do this separately. That's a lot to work on. So that's n is less than or equal to 100c times square root of n. And then I can divide by, so this is multiplied by 100 on each side, and this is divide by n on each side. that gives me, let's see here, divide by square root of n, sorry. I'm going to get rid of the square root of n on this side. Well, n to the 1 over n to the 1/2, you subtract them, right? So you have square root of n again, n to the 1/2, less than or equal to 100c. Okay? And interesting. Well, then we have that if we get rid of the square root, if we square both sides, right? We end up with n less than or equal to 100c squared, always, okay? And this is always true as long as n gets bigger than n naught. And this is where the contradiction happens. We have just said that 100 times a constant squared always bounds above the number n, which is allowed to vary. Do you see how that's never going to be the case? But c is a constant. You can always find a bigger n. If you go far enough, you'll find an n that's bigger than 100c squared for whatever c you picked. Just choose n to be c plus 1 or something, right? And times 100 squared. That's a contradiction. I hope you see that. A constant will never bound above anything, but we've just found that it would. That's silly. So that proves that this is not bounded above by square root of n. It's a smaller function, in fact. Okay? So that is how to prove this by contradiction. Do yell at me if you have any questions about that. That is a very nice proof. Gives us some practice using proofs by contradiction all over again. And we're getting more experience using our big O notation, what it really means, its mathematical definition. Okay? So I think we're ready. We're comfortable enough with big O now to talk about the other ones. There's big omega and big theta. All right? Big theta is usually the one that we care most about in computer science, but we have to learn about big O and big omega first before we get there. All right? So big omega is kind of the opposite of big O. Big O was, this thing was a upper bound, but for big omega, the function that you put inside of the omega is a lower bound. Okay? So here's the definition of big omega. F is big omega of some other function g if there are constants c and n naught, surprise, surprise, such that f is bounded below now. F is bigger than, f for some n, is bigger than c times g of n whenever n is bigger than that starting n naught. Okay? So this just means that g is a lower bound now. It's on the lower side. G is a lower bound for f. Oops. So all this means is there is a certain point, n naught, such that c times g of n, for your carefully chosen c, is always below f. See how it's always below? That means you found a lower bound. All right? So for example, f of n is big O, or big omega of n to the 5th. That's still fine to use the same one. It's just, okay, the constant can be 1 now. See that? These are all lower bounds. Same with it's big omega of n to the 4th, because that's a slower growing function. You can find a good constant still. Same with n cubed. It's a slower growing function. These are all lower bounds for the original one. Okay? I hope you see that. That's big omega. That means you found a lower bound. And I'm going to jump right into big theta again as well, because if you bring together big O and big omega, if you have a function that is big O of a g and also big omega of that same function g, maybe for different constants, right? Then you know that it is big theta. Big theta is the combination. F is big theta of g, if and only if it's big O of g and big omega of g at the same time. Okay? So if you unpack these definitions, you just have both of those true. That means that there exists constant c1 and c2 such that, also n naught, such that f is bounded on both sides, right? Below by big omega for a certain constant, and above by big O, just normal big O, for another constant. F is sandwiched between them as long as n is greater than or equal to some n naught. So you find a good one. Here's your n naught, such that it's always the case that f for those carefully chosen constants, it's sandwiched between the same function. Isn't that cool? So it's bounded below by c1 g of x, and it's bounded above by c2 g of x. And as long as n is bigger than n naught, that sandwiching is never going to stop. It's always bounded in between. Okay? So that means that g is both an upper bound and a lower bound for f, which is very powerful. It's called the tightest possible bound for the function f. Okay? Can't find a better one, according to our definitions. All right? So you now have only one choice for things involving big theta. And this is why we care about big theta in computer science. Usually when people say big O in computer science, they mean big theta because they're asking for the tightest possible bound. Okay? So 2n to the fifth, that is big theta of n to the fifth only. There is no other option to put there. Okay? All right? There is no other option. You cannot try n to the sixth or n to the fourth, because then one of these, O or omega, sorry, those are hard to say, either O or omega fails. It does not work. Okay? Same with this one. If f is 2n squared, then it's big theta of n squared only. That's the only way you can have, for carefully chosen constants, to be sandwiching this function on both sides by something. Okay? And this is really why these rules aren't really giving you big O. They're more accurately giving you the big omega form of that function, right? Because for big O, you can always just pick something bigger. Like, it also works for x cubed here for big O. But for big theta, it's forced to be x squared. All right? I hope you see that. So, yeah. Anybody who's asking you in an interview for the big O of a function, they really want big theta. All right? So that's that. And now I want you to try this. Characterize the rate of growth for each function f by giving a function g such that f is big theta of g. And so really, you're just going to follow these rules again. But that is why we follow them. That gives us the tightest possible bound. That's lovely. Okay, so give this a try. All right, so we have to find the biggest term, which one grows the fastest. Taking the log of a log is quite small compared to this one, and constants are also small. So this wins out, n log of n wins out, and we also drop the constant. Okay, so this is big theta of n log n. Okay, it's log base 2 whenever you write log in computer science and not say anything. It's usually talking about log base 2. And then for b, what is it? Well, n log base 37n. That also works. But let me show you this. In computer science, we don't really write the base for a log when we're talking about big theta. It's unnecessary, in fact. I can just say n log of n here. And the base doesn't matter. It could have been imagined to be 2, could have been still 37, but the base doesn't matter. And let me show you why. Base doesn't matter. So we usually just omit it all over the place. Like, I don't even say it there usually. So the base doesn't matter, and let's see why. Because the base is just a constant. The log base 2 of some number, that's equal to the log base 3, right? You can change between bases very easily by multiplying by, what is it, log base 2 of the number 3, and this is always just a constant. Constant. So you can always switch between bases using a constant, which means you can get rid of that constant. And so people just like to write log and not give a base. There's no need to. Okay? Sorry for my squeaky chair. Let's try this one. N to the 21 plus 1.1 to the n. Which one grows faster? And it might seem wrong, but this one is the bigger growing function. It's the faster growing function, and I encourage you to graph it. This is like, instead of 1.1, imagine it as like 2 to the n. It's exponentially growing. N is in the exponent. That is always bigger than a polynomial involving n with a constant power. Okay? When it's a variable power, that wins out. It's exponential. 1.1 to the n. All right. What about this one? Which one wins? This is, again, just big theta of n cubed. That's our normal rule following. Okay? So, yeah. just using those rules, it was really giving you an answer involving big theta. That's the tightest possible bound. Okay? And now, let's actually use the math. Okay, so going back to the real definition involving all this, or this one, either one, involving the real definitions of these functions. So big theta, big omega, big O, prove that f of n, which is this, is big theta of n cubed, right? That one wins out. And tell me exactly why. I want you to find C1 and C2. I want you to find n naught and prove that it follows and it meets the definition of being big theta. Okay? It must satisfy the definitions for big omega and big O. So it's a lower bound, it's an upper bound. So give that a try. Okay? See if you can prove this. All right. So let's see what we have to do. We have to bound above and below this guy. So using our tricks from before, well, for big omega, it's very easy, right? I can just write this, n cubed plus 3n squared plus 4. A lower bound for this is, okay, these are always making it bigger, so let's just get rid of these. It's always the case that n cubed is less than or equal to n cubed plus extra positive stuff, right? So this always works, right? This works when n is greater than or equal to 0. It's always true that this is true. And that means that here's a nice constant out in front of n cubed. It was just, I needed to find some constant C1. I didn't need one. It's just 1, right? I can just make it 1. And this is a true statement. Yeah? So that gives me big omega. I know that f is big omega of n cubed. Okay? And then I need to also prove that f is big O of n cubed. So I need to find an upper bound now. N cubed plus 3n squared plus 4. What's an upper bound? You can use my little pattern involving n cubed, right? So I need to find some C2 times n cubed. What's a good one to use? Well, let's do it this way. Let's be like n cubed plus 3n squared plus 4 and change all of these things out inside of anything that's not n cubed to n cubed. And so then we have n cubed plus 3n cubed plus 4n cubed now. I gave everybody an n cubed. It's always bigger, right? And again, this is always true. This works when n is greater than or equal to 1 now. Okay? Because that 4, when it was 0, it didn't really work when it was 0, but once it's 1 or bigger, it's always going to work. Okay? And this is equal to 8n cubed, right? 4, 7, 8. And there's my nice little constant, C2. So my n naught, as long as n is greater than or equal to 1, 1 can be my n naught, and C2 can be 8. That's the number that I'll multiply n cubed by to get something bigger always. And so I've just proven that it's big O. I've proven that f is big O of n cubed now. And so, yeah, that's all I really needed. I found that C1 was equal to 1, C2 is equal to 8, and n naught is just the bigger one. Like this part works when n is greater than or equal to 0, but this part only works when n is greater than or equal to 1. So I need to keep the bigger one. Okay? I want them both to work at the same time, so n naught for the whole big theta better be the harder one. It better be 1. Okay? That's going to make it work. So therefore, bringing all these together, f is big theta of n cubed. QED. So we found all those particular constants, and it all worked out. Okay? That's what we needed to do. And that is the key. All right? So let's take a look at our time. Yeah, we have a little bit to move on into algorithm complexity, because this was just function complexity. Like how do you come up with n cubed plus 3n squared plus 4 to represent an algorithm? We still need to go there, right? So let's do that. Let's actually go there and talk about the complexity of algorithms. How do we come up with a function that represents something about how our program is executing, how our algorithm executes? How do we come up with a function and then apply big O to that? What does that all mean? Okay, so let's talk about it. So we would like to find the computational complexity of an algorithm, which just means, like, how fancy is it? How many resources are being used by the algorithm as it's running? Okay, that's what it means to ask about the computational complexity. And resources is a very vague term. There are a bunch of different kinds of computational resources that we can ask about and analyze when we analyze our algorithms. So let's be more specific and pretend that we care about just these two in this class. We care about the time complexity and the space complexity of an algorithm, okay? And so time complexity, that's the one we care most about usually. That's the amount of time the algorithm needs to run given an input, given a certain size of the input, okay? And instead of asking like, well, let's time it on my CPU, it took 42 minutes to run this algorithm. We don't like that. Instead, we want to make a mathematical expression that involves the number of basic operations, for some definition of basic, that it takes in order to run that algorithm. And that will be the same regardless of your processor. Like if you have a 1.5 gigahertz processor, it's obviously going to run faster than a 3.5 gigahertz processor, the same algorithm. But if we express it instead of like clock speed, instead in terms of basic operations that are shared among those processors, then we have a better idea of how complex an algorithm is. Okay, how many steps is it really taking? That's another way of talking about basic operations. How many steps does the algorithm take to complete for a given size of the input? And then we can also talk about the space complexity of an algorithm. That involves how much memory does the algorithm need in order to execute and give back an answer, because it needs maybe a lot. It takes a lot of space to think about its answer and compute it for some algorithms, as opposed to others where it just takes a few variables, okay? And so we can count the number of bytes, for example, that it takes to store all the memory that we need as our program is working. So maybe like if it needs to make an array, we have to worry about how big that array is going to be, things like that. Okay, so those are the two kinds of complexity that we care about. And the whole point, the whole reason we had this section on all these big O, big omega, big theta, asymptotic complexity of functions, is that we want to translate our program's basic operations, our program's number of bytes that it's using to execute. We want to make functions that describe those things, the amount of resources used, given a variable input size. This is how it's going to come full circle, right? We're going to make a function that keeps track of, as our input size increases, how much resources we're using, how much time we're using, how much space we're using, okay? And then we can finally use big O and big omega and big theta, and that gives us something to work with and actually asymptotically analyze, okay? That's where we're going. That's the point of all of this. Hopefully it makes a bit more sense than it did in 41, okay? So let's have an example. Let's have actual C++ code for once. Let's analyze the running time of summing all the elements in a vector. So here is a nice vector sum function. It takes a vector by reference. It computes the sum of all of its elements. It gives back that sum. Let's talk about the running time, okay? Let's do running time complexity first. So we'll calculate the number of basic operations it takes to complete and execute this algorithm, okay? So we're going to come up with a formula based on n, where n is the size of our vector. Usually that's what we talk about. Let's assume that the vector is size n. So we're going to come up with a formula based on n for the number of basic operations that it takes to run this code, all right? And n is the size of the input, it's the size of the vector. Let's just remember that. So what is a basic operation, you might ask? Let's define it to be this. Let's say that a basic operation is any of these things. It's an assignment statement that takes one basic operation to assign a value to a variable. It takes one basic operation to return a value from a function. Any mathematical operation like plus or times or divide or mod, that takes one basic operation to perform that in the CPU. looking up the value of a variable. Let's assume that takes one basic operation to go to memory and look it up. All those things. And this is kind of sweeping a lot of stuff under the rug, but this is a good starting point, and it's not really going to matter because constants go away anyways for our definitions of our big O, big omega, and big theta. So assume that basic operations are these, and we'll count now. We're eventually going to count this. And so at the end of the day, really, once we get past this nitty-gritty of counting every individual thing, you'll learn that really just a single basic operation is any line of code that doesn't call any functions or do anything weird like looping or things like that. Okay? So that is how we're going to analyze our function. Let's use that definition to count the number of basic operations. Okay? So here we go. This line is an assignment statement. So it's going to take the number 0, put it into sum. That is one basic operation. I'll take one basic operation. It's only ever going to run once. Okay? And then we're also going to set n to be the size of the vector. Let's assume that v.size, calling that and getting back an answer, takes one basic operation, and then assigning it into n is another basic operation. That gives me two basic operations. Okay? Then at the very end, we're going to return sum, which returns the value. It's one basic operation to return from a function. Maybe technically it should be 2, right? Because we have to look up the value of the variable and then return it. That's fine. Sure. That works. And then let's talk about these. How many basic operations do these take? So the for loop, it starts with this, right? And this only happens once. That's the initialization of the for loop. So this is one basic operation to put 0 into I. It's an assignment statement. Then we have to do all of these. Oh man, oh man. Well, what needs to happen here? We have to look up the variable I. We have to look up the size of it. And then we have to compare. So that's 3 basic operations, essentially. Call, look up the variable, do the comparison. 3 basic operations. I++, that's equivalent to I equals I plus 1. So a lookup, an addition, and an assignment. 3 basic operations. Same with this. This is going to be v at I, get that. Let's assume that that takes one basic operation just for fun. Essentially it does. So that's 1 to get that value, and then 1 to look up the sum, and then another to add into sum, and then another to assign it, right? So a lookup, a call, an addition, and then an assignment. So that's 4, I guess, 4 basic operations. And this is all going to repeat. Oh man, all this keeps getting repeated. How many times? It's about n-ish times, yeah. That's mostly what's going to happen. Let's say that this is going to repeat about n times. Because I is going to go between 0 and strictly less than v.size. And so essentially that's going to take n times to complete. So the number of basic operations for this whole algorithm is going to be, well, these just happen once. 1 plus 2 plus 1. Plus this 1 right here. No, we already did that, sorry. And then we have to do n times this. N times 3 plus 4. And then at the very end, actually, we have to stop the loop because I got too big. It got to be equal to v.size, and that's going to stop the loop. So we have to actually compare one last time. So that's going to involve 3 more basic operations just to stop the loop. And then we return sum, that's 2. Okay? So the number of basic operations is this. Okay? So the function that describes how many basic operations for an input size n is, let's try and compute this. It's going to be 5, 8, 9. So something plus 9. And then this is 7, 8, 9, 10. 10n plus 9. Okay? And so, what is that? But big theta of n. This is a linear algorithm. You see that? So that is our final answer, because we came up with this. That is the number of basic operations that it takes to run this algorithm. Crazy. And that was what it took to figure it out. All right, so we just analyzed the running time of this function. Wasn't that cool? So this is where I think I would like to stop. I will come back next week and we'll talk about like different kinds of analyses. You can talk about the worst case analysis, the best case, the average case. We care most about the worst case in this class. And then we'll eventually get into, analyzing code that we've written already. Won't that be fun? So look forward to that, and I will see you next week.